Hello, everyone, and welcome back to Black Harbor's Advanced Tara series. Kicking things off today, focusing on threat modeling methods with Justin Woods leading. Justin?
Hello, thank you again. Let's get right on into this. So today we are focusing on threat modeling methods. There are two main ways of doing this. The first one we will cover is going to be a attack tree methodology and going through the attack steps. So before we even really get into the threat modeling specifics, we got to figure out kind of the higher level, kind of what's going on here, what are we looking at. So first, we want to start by having a step-by-step procedure to identify threats and vulnerabilities. So all this is saying is we need to have a kind of good understanding of how to actually look at the different parts of the vehicle and what we would want to protect and the different threats that there might be for them. So you want to identify those assets, be it a program on an ECU, like a specific function it might have, the ECU as a whole, perhaps the connection between two ECUs and that data. Anything like that might be an asset depending on what can kind of be done with that, right? Then we also have creating architectural overview, including data flows, etc. So what this is saying is once we know all of the different components of the vehicle or of the specific feature that we're doing a TARA on, we can have a kind of model and an overview of how everything is flowing together so that when we do get to this next step of identifying threats, vulnerabilities, and requirements, we're able to use that understanding of how things are moving to know how any attack may propagate throughout the system or can be affected from one ECU to another. And then we're also looking at the different levels that a threat might affect. So it might be from a component level, a subsystem level, or a full vehicle level. So something component level would be something like reading data off of a, let's say, a infotainment system, perhaps the Bluetooth contacts on there, right? Or the contacts on a phone, perhaps you're able to get that through Bluetooth, and that would be a component level attack. And then a subsystem level attack might be something like the ABS, though this would also kind of go into the vehicle as well. So the subsystem of a ABS module might be something like just looking at the speed. Maybe it's using the connections there for that as well, and not having a separate wheel speed sensor or something like that. And we're able to get that speed from there and perhaps use that in another attack, or for some reason, maybe somebody just wants to know that. And then a vehicle level attack would be something like using that same ABS module, but now not just looking at data, but actually messing with stuff. So even something as simple as that vehicle speed, perhaps you're able to tell the vehicle that different tires are going at different speeds or different wheels are going at different speeds, leading to the module trying to overcorrect something that's not actually happening. And then, of course, that leads to vehicle instability, which would lead to, of course, that vehicle level kind of threat and attack. So we'd want to then kind of measure and analyze the types of severity and impact of the threat on a TOE, this being the target of evaluation. Uh, Again, whether that be feature, ECU, or data, whatever it might be. So, of course, with that ABS overcorrecting, perhaps it might lead to an accident, right? So that'd be a pretty severe impact. And on the component level where a file is read, that would be lower on impact, but it does have a big impact in privacy. So to kind of level out a little bit in terms of how important it would be to protect it. Then we want to define the security objectives with the CIA triad being confidentiality, integrity, and availability. So we see kind of what threats may exist and then how we can kind of protect against them by using the different kind of cornerstones of the CIA triad. Some of those methods to do that are, as I'd mentioned, the attack tree and the stride methodology. At Block Harbor, we use the stride methodology, but we will also go over the attack tree to begin with here. And then at the bottom, you can see kind of a general outline of how TARAs are performed. So first, you're going to look at kind of the damage scenario. So what could happen? So the worst case for that vehicle level being possibly an accident. And then the threat analysis of, okay, what kind of attacks and threats might be out there that could cause that. And then we further go into the risk assessment of kind of how likely is it that those attacks could actually occur. So different feasibility ratings and the impact analysis together there. And then lastly, some cybersecurity requirements to try and mitigate from those threats actually occurring. So anything that we find that initially might have a high risk, we want to try and lower that as much as possible and not just ignore it, which is why, of course, we want to make some requirements there. So now into the attack tree methodology. We're going to start off by looking at the vehicle's attack surface. So there are, from before a vehicle is even made, there's the engineering supply base. So this is talking about the component software, hardware, and the manufacturing that goes into it. Any attacks done there may lead to a kind of widespread lack of cybersecurity. Then we also have any type of remote attacks to the vehicle. So this is going to be for the connected vehicles that have a back-end server infrastructure, as well as any updates that might be able to be sent to a vehicle, as well as diagnostics that could be done. The diagnostics is important because it is kind of PII in a way that GPS is considered to be PII. So any information like that on where somebody actually is located might be able to be found through diagnostics, which is something you definitely want to make sure is protected. And then proximity. So any type of proximity attack, this would be such as a Bluetooth attack on the ABS module. Some vehicles nowadays also have Wi-Fi, so trying to connect to that and mess with it there, as well as cellular. We actually had a event that we went to and demonstrated a attack where we pretty much acted like the cellular tower and were able to look at all the data going to and from a vehicle. And then V2X, so any vehicle to infrastructure, vehicle, what have you, communications, that is also going to be a avenue of attack that somebody might try and capitalize on. And then sensor data, be that camera, infrared, LiDAR, whatever it may have, any type of sensor, data can either be spoofed or things can be shown to it to intentionally mislead it, like painting speed limit signs incorrectly and changing the values there, where perhaps the camera will look at that and take that as the actual speed limit rather than using some other type of knowledge base as to what speed it should be going. And then a mobile app, so just another route of connection to the vehicle that maybe you can start the vehicle, or like with some cars, you can have them come straight to you. Anything like that, you would want to have pretty protected, of course. So that mobile app needs to be pretty locked down. And then locally, when you're actually connected to the vehicle, you've got the entire network within it. So the CAN bus, as well as the LIN and automotive Ethernet. So all the different lines of communication there are able to be attacked, of course, and therefore an attack surface. And then we also have the USB. We've got even the audio jacks. You've got physical attacks even that can be done. There's all sorts of different things that can be done, both locally, remotely, just near it, and even before you even get to the vehicle. So these are all things to consider when we're creating these kind of attack steps and thinking about what type of attacks may happen, especially when we're looking at a specific feature. Some features may be only attackable locally, but perhaps they connect to an ECU that is able to be updated remotely, right? So got to look at all these different aspects and figure out kind of what's going on and how to protect it. So going into the attack tree methodology a little deeper now, this is talking about a more quantitative approach. It has a graphical representation of attack possibilities with a tree structure. So as you can see on the right here, we start at the top here, the root of the tree, kind of upside down, right? Kind of upside down tree is going to be the security goal. So what are we trying to protect? So in this case, we have a headlamp feature, and we're trying to ensure that integrity and availability is maintained. And then the next step here would be the threat scenario, kind of just going down the tree, of course. So perhaps there is a spoofing that is able to lead to loss of integrity of the data communication. And then, of course, below that, we have kind of what actually might cause that, right? So there's a list of attacks, be it compromise the navigation ECU from cellular, perhaps through malicious control signals, spoofing the LAMP request off. All of these different types of attacks could lead to that same threat scenario. And then with all that together, we are able to say, okay, here's the different attacks, and these go against that security goal, right? So from that, you figure out how to mitigate those attacks through those cybersecurity requirements. So we want to look here and kind of determine which actions should be prevented. So you identify the possible attacks, as we had mentioned. You want to think of kind of how an attacker might come at the vehicle, what's going to be the easiest for them to do, uh, what's going to kind of take the least amount of time, right? Because as an attacker, while yes, there will always be some level of insecurity in vehicles due to wanting them to be kind of accessible, right? We know that there will be some flaws, but we want to make sure that those flaws are extremely difficult to get to. So if we say, hey, the only kind of attack that's possible here is going to be something that takes a year to do and millions of dollars of equipment and man hours, right? That's not something that is going to need to be necessarily protected. However, if you have something that somebody can buy, like a $50 little radio, and spoof the Bluetooth to your ABS module and disconnect them or tell them different information, that's going to be something that we want to say, hey, this matters, do something about it. And then kind of validating that attack path and making sure it's actually feasible and possible is another step here as well. A lot of times this will have to be done with the feature owner themselves, just trying to figure out how likely this actually is to be possible. And again, here we can kind of see how security is not necessarily a product, but more of a process. So you have to integrate security from the beginning, not kind of ad hoc, right? Because if you try to ad hoc the process, you end up with a subpar secure component compared to a fully robust component where you're able to make sure that everything is secure from the get-go and throughout that whole process of, hey, here's the different attacks, here's the different requirements, integrate all of those, and then create the product rather than creating the product and then going back at it and going, oh, there's all these different issues here, and let's try and fix them now. And then you just keep kind of creating the next version, and then that has these new vulnerabilities, right? So you want to kind of get away from that and think of it more as a process rather than just a one and done type of a thing. And then kind of breaking this down as we kind of went over before, that first step in the kind of attack tree here, not the goal, but the attack tree itself is going to be kind of the attack objective. So what is it they're trying to do? This is associated with severity as well as kind of the damage scenarios. So damage scenario and threat scenario kind of go back and forth here. We can look at the severity in terms of the SFOP, so safety, financial, operational, and privacy is how we would look at these. We go into this deeper in some other courses on here, but that's kind of what we would associate with this specific portion. And then next would be the attack path. So the actual attacks that are being done. So again, we're looking here kind of the feasibility of them. How likely or feasible is it that a attacker might actually do this? And then the intermediate steps kind of follow after that of trying to figure out how likely it is, who's going to try and do it, talking with the feature owner, see kind of what requirements we can do to mitigate those, and kind of just so on and so forth, right? Then there is the CVSS, the Common Vulnerability Scoring System. We use three metric groups here, the base, the temporal, and the environmental. And feasibility is determined based on exploitable metrics or exploitability metrics. This is coming out of ISO 21434. So we're going to look at the attack vector, the attack complexity, the privileges required, and user interaction. As you can see down here, we have the actual exploitability, not algorithm, but there's algorithm, right? The whole process here it should be dot, but 8.22 times the vector, complexity, privilege, and then the user interaction. And we can see up here, kind of the base metric groups here has a kind of good understanding or a good little example of what these different groups are. So in the base metric group, we have some exploitability metrics as well as the impact metrics here. Then we're trying to look at a specific attack. We want to see what type of attack vector there is, the complexity of it, what type of privileges are required, the user interaction, again, it's all of these, and then the scope of all of it as well, kind of what is it that we're looking at. And over here for the temporal metric group, we want to look at perhaps the code exploiting it, and then kind of the remediation level, as well as the report confidence. Then we go over to the environmental metric group. We have the modified base metrics, confidentiality requirement, integrity requirement, and the availability requirement. So the CIA triad here is the kind of securing of the system, right? Trying to ensure that those requirements are being met to make it so that these attacks are a lot less feasible. So now going into the STRIDE methodology, what we actually use here, this is going to be more of a qualitative threat analysis method. This is going to be used for identifying threats according to the purpose of the attack. And instead of every type of attack possibility, it is more concise. So it limits the types of threats into these 6 different categories, hence the STRIDE name, right? So we have the spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. Pretty much we break it down this way because it is more repeatable. The efficiency and effectiveness is based on a known design. It's relatively easy to document compared to the attack trees that can get quite robust and hard to follow. And the controls can be directly associated with identified vulnerabilities. So if we see, hey, if somebody has access to this CAN bus, they're able to spoof this specific request as it has no type of counter or other type of security mechanism in place. Then we can say, okay, let's create a requirement to make that not the case, right? Maybe we want to add some other type of encryption counters or authentication in place to ensure that it can't be spoofed that easily. Right? So we can identify and track those things very easily there. Here's an example of some STRIDE threats on assets. So for a spoofing threat, a description might be that a threat actor pretends to be something it isn't. And this might be on an asset like the vehicle sensors or the ECUs. And the attributes that this kind of involves and goes against out of the CIA triad would be integrity. Then we also have the tampering, which would be a attacker actually changing the data. So not just acting like they're the one sending it, but actually changing it. So this is going to possibly affect the ECU software. And again, this would be an attack on the integrity of the data. And I'm not going to read through all of these. You guys can pause the video and read through them yourself if you would like to. We will continue on now. So here is a kind of fleshed out example. Here we have a threat description of or damage scenario, threat scenario, all kind of the same thing here. So a data flow or CAN signal is potentially interrupted. So this would be a denial of service attack. The impact in this case may be high, and the feasibility would be moderate, and the risk would be moderate. And then out of that, we can determine that this is a pretty significant issue. So our security goals for this would be to try and prevent a denial of service, and then to prevent unauthorized remote access and control of the vehicle and vehicle systems. So we don't want anybody to be able to perform this remotely, and to further acquire the security and attributes to put in place with this vehicle. We want to make sure that these goals are reached through adequately designed requirements as well. And then we do also have damage and threat catalogs. They do provide quite a bit of benefit in the tool that we use currently. We use the Akindu security analyst, and we're able to kind of document and keep our originally created threats, as well as a fleshed out catalog created by others, and we're able to use them to kind of already have a good understanding of the equipment, time, knowledge, uh, experience required, and time to complete. All of that can be assumed or used from what others have gathered in the past, and we're able to assign kind of damage scenarios to these threat catalogs and get them completed kind of more quickly and have it for the future as well. And that is it for today. Thank you, everybody, for stopping by and watching this. Hopefully you learned something, and we look forward to seeing you again.
Justin, what language is that in?
I don't remember.
We'll have to Google that. All righty. Well, thank you, everyone. Thanks again, Justin. Catch us for the next episode. Chat soon.
Thank you. Bye.